This is B. Naresh, working as assistant professor in AC department. And today's topic is two-level clippers. So in the last session, we observed that what is a clipper. In that, we observed that what is a positive peak clipper and negative peak clipper. We know that the clipper is an electronic circuit. It can be used to remove or attenuate or limit some portion of given input signal. So for this case, we are going to use the semiconductor diode. So by using the semiconductor diode, we are designing the clipper circuit to remove or attenuate or limit some amount of portion in terms of voltage for a given input signal. But coming to this two-level clipper, so in this case, we are going to cascade the two different independent levels. Means in a positive peak clipper, so by using this positive peak clipper, it removes the positive portion of given input signal. Suppose if you are using the negative peak clipper, it removes the negative portion of a given input signal. Or if you applied some amount of the reference voltages across the positive peak clipper or a negative peak clipper, it removes the positive peak along with some reference voltage. Or suppose if you are using the negative peak clipper with reference to the DC voltage, then it also removes the negative portion with respect to your reference voltage here. So that is the reason in this two-level clipper, we are cascading this positive peak clipper as well as the negative peak clipper with respect to some reference voltages here. So based on that reference voltages, this two-level clipper removes the some amount of the portion with respect to your applied DC voltages, either in a positive portion or in a negative portion or in the combination of positive as well as your negative here. And from that point of view, this type of the clipper is called as the two-level clippers here. So to design this two-level clipper, here we are going to use the positive peak clipper as well as the negative peak clipper. So with respect to these two combinations here, then we are adding the some amount of the DC voltage across the positive peak clipper as well as the across the negative peak clipper, and that resultant response of a circuit is called as the two-level clipper here. Now coming to you, first we'll see this. So how we are going to design this two-level clipper. And in this example, first I'm going to remove some amount of the portion in a positive portion, as well as I'm going to remove some amount of the portion in a negative peak signal here. That type of the waveform means it limits the amplitude in a positive portion. Similarly, it also limits the amount of amplitude in a negative portion. From this point of view, the given circuit is also called as a voltage limiter here. Now, let us consider for this two-level clipper. So here, I use the two types of the clippers, positive peak clipper as well as negative peak clipper. So if you remove this VR1 and you remove this VR2 and this D1, the way of approaching this D1 diode toward this ground potential, and based on this utilization of the D1, and here the circuit is called acts as a positive peak clipper. And if you are utilizing the like this fashion with respect to D2 diode, and the VR2 is a remove, and D1 and VR1 is a remove, then the circuit is acts as a negative peak clipper. Suppose if you remove this D2 and the VR2 and the VR1, only the D1 is connected to ground potential, then the given circuit is acts as a positive peak clipper here. And here we are combining these two, positive peak clipper. So the D1 is acts as a positive peak clipper, and the D2 based on this D2 construction, that is acts as a negative peak clipper, means we are combining positive peak clipper as well as a negative peak clipper. But for this diode D1, we added some amount of the reference voltage, and that reference voltage is a DC reference voltage. Here I represented as your VR1 here. And from this point of view, from this node, if you remove this node here, if I remove this one, this portion, now this circuit is acts as a positive peak clipper with some positive reference voltage here. Similarly, if you remove, so if you remove this D1 portion along with this VR1 here, now this circuit looks like a negative peak clipper with a negative reference voltage here. So in this case, if you want to satisfy this two level clipper, we are combining this positive peak clipper with positive reference voltage and negative peak clipper with negative reference voltage with resultant. Then we are going to observe the response across this parallel node, and this type of the circuit or a clipper circuit is called as the two level clippers here. And let us assume the given input signal here, it is represented as Vm sine omega t. So the magnitude is represented as Vm. It is a linearly varies with respect to your time period here. And again, the note point is, so here I consider this VR1 is equal to VR2, but the magnitudes are different here. I consider the same amount of the reference voltage across the D1 as well as across the D2, but the magnitudes are different here. So means VR2 is represented as negative magnitude and a VR1 is represented as positive magnitude. So but the amount of voltage is the same across this VR1 and your VR2, but the polarities are different. So this VR1 is a positive magnitude and the VR2 is the negative magnitude here, but the amount of voltage is your same here. Just you remember this point here. Now again, before going to this operation, first we need to recall the diode operation here. We know that, so if you consider the diode, and again diode contains two electrodes, one is anode, another one is cathode. And we know that when the diode is conduct, generally if the anode is made with the positive pole of the battery and a cathode is connected with the negative pole of the battery, then we can say that that particular diode is entered into the forward bias here. So under this forward bias, diode is acts as a conducting. So if the diode is a conducting, the amount of the current flows across the PN junction diode or in the current flows in a given network here. Similarly, if the diode is, so in the diode, and this is again anode and this is the cathode, if anode is connected with negative pole of the battery with respect to the cathode, means cathode is connected to positive pole of the battery and anode is connected to negative pole of the battery, then we can say that at this point, at this biasing, diode is enters into the reverse bias here. So if the diode is a reverse bias, means there is no conduction takes place across the PN junction diode, hence the current flowing across this device is represented as your zero. Under this condition, this diode is replaced with a open circuit. And when the diode is a forward bias, under this condition, diode is replaced with a short circuit here. But in a practically, it is a replaced with a short circuit along with some current voltage. Based on these two analyses, we need to identify when the diode is conducting and when the diode is not conducting. So means that from this analysis, how much anode voltage is required to make the diode is conducting state here. From this point of view, you should remember this point, the anode voltage. So where I represented the V suffix A means the anode voltage must be greater than or equal to cathode voltage. The anode voltage must be greater than or equal to cathode voltage. Then only we can say that diode is conducting state here. So means under this condition, diode allows the conduction across the given network here. And similarly, if the anode voltage is less than of cathode voltage, then the diode is non-conducting state here. So means at this point, diode state is represented as your off state here. If the anode voltage is greater than or equal to cathode voltage, then diode is acts as a conducting state. This state is represented as your on state here. Under this on state, the diode is replaced with the short circuit here. If the anode voltage is less than of cathode voltage, the diode state is represented as non-conducting. Hence, under this non-conducting, this state is represented as off state here. So if it is off state, it is replaced with the open circuit model here. So based on these two representations, now we are going to analyze the how this given circuit is acts as a two-level clippers here. So for this case, I consider the same circuit. Hence, across this, now we are going to observe the output voltage or output response. It is represented as your V0. So during this positive off cycle, then again, here I made the one condition when if the Vi is greater than or equal to VR1. But what we assumed here, the VR1 and the VR2, the amount of voltages are same, but magnitudes are different. VR1 is the positive magnitude, VR2 is the negative magnitude. When an input is passing towards the VM signal, let us assume that if the input voltage is greater than or equal to VR1, means your input signal is connected to this node, means Vi is passing to here, and again Vi is passing to D2 here. Means here at this point, for the D1 diode, the Vi is connected across the anode. For a D2 diode, input voltage is passing through the cathode. But here, this side, what happens here? So, anode is connected with a VR2 for a D2 diode. For a D1, cathode is connected to VR1 here. The difference, receive difference voltages here. And these are the constant magnitudes here. VR1 and the VR2 is the constant magnitudes here. And we assume that when an input signal reach towards the VM, let us assume that if the input voltage is greater than or equal to the given DC reference voltage 1, that is VR1, means what happens here for diode D1, anode voltage becomes greater than of cathode voltage here. So when for a diode D1, if Vi is greater than or equal to V1, so what happens at this point? The anode voltage means input signal is passing through D1 of anode. Similarly, the input voltage is passing through D2 of cathode. At this point of view, whenever the input signal just crosses the magnitude of given DC reference voltage 1, now it satisfies this condition. Thus, anode voltage becomes larger with respect to your cathode voltage. Now we know that if the anode voltage is greater than or equal to cathode voltage, then we can say that diode is in a conducting state here. So from this point of view, D1 is acts as a conducting state here. So if it is a conducting state, we can replace with the on state here. So on state means it should be replaced with the short circuit. Similarly, let us assume that, so this is the positive magnitude. We are assuming that Vi is greater than or equal to Vn, means Vi is passing towards the Vm. So at this point, so what happens here, the positive magnitude for this diode D2, for diode D2, a positive magnitude is connected to cathode of D2, and a negative voltage is connected to, this is the constant difference voltage, and this magnitude is represented as a negative magnitude. And at this point, this D2 point, the negative magnitude is passing through anode of D2, but the positive magnitude is passing through the cathode of D2. Hence, so what happens at this point? Anode voltage is less than of cathode voltage under this condition, when VA is greater than or equal to VR1 condition here. So that is the reason more positive voltage is passing through cathode of D2 compared with the anode of D2. That is the reason it satisfies this relation. If the anode voltage is less than of cathode voltage, what happens here? Here diode D2 becomes non-conducting state here. So here the diode D2 becomes non-conducting state here. So if it is a non-conducting state, so means diode state is represented as off state. So if it is off state, it is replaced with the open circuit. So based on this given input voltage, if the input signal is passing through towards a VM, whenever that input voltage just crosses the given DC reference voltage, positive reference voltage, we observe that the diode D1 is acts as a conducting mode and the diode D2 is acts as a non-conducting mode. Hence, we need to replace the D1 and the D2. So here the D1 is replaced with a short circuit model. Why? Because of that, the diode D1 is acts as a conducting mode here. And with respect to this applied input approach, here the diode D2 is acts as a non-conducting mode. Hence, D2 is replaced with a open circuit. So from this, I'm going to redraw this equivalent model. So this is our circuit, and based on your approaching, so when VA is greater than or equal to VR1, so what we observe here, D1 is replaced by on mode, means short circuit path. So hence, here I drawn the D1 is replaced with a short circuit path. At this given input voltage, the diode D2 is acts as a non-conducting, hence it is replaced with a open circuit. So hence, the D2 is replaced with a open circuit. So from this equivalent circuit, now we need to identify this output voltage. So what is output voltage? Now we are going to measure this output voltage with respect to parallel nodes. So this output voltage is parallel with this another voltage source is VR1. So we know that the parallelly voltage is the same. Hence, from that representation, V0 is represented as your VR1 here. So hence, if Vi is greater than or equal to VR1, the output voltage across the two-level clipper circuit is represented by VR1. That is a constant voltage, that is nothing but a DC magnitude. Similarly, now we need to analyze if the Vi is less than or equal to minus VR2. So we need to take your input signal is less than of minus VR2. So what happens here? Your input voltage is less than of minus VR means, and your input signal now passing towards minus Vm here. your input signal is passing towards minus Vm. At this signal, let us take this is my VR2, and that VR2 is represented as a negative magnitude. So from this point of view, so from this VR2 to minus Vm means your input signal becomes your less area. So let us take, and here if you observe from the circuit, the D1, if you consider across the diode D1, so in a diode D1, anode is connected to means when this input signal is less than VR2 means when the input during the negative up cycle, input is passing towards the minus Vm, and whenever it crosses the negative DC reference magnitude, then your signal becomes lesser of the given DC reference source here. In this point of view, whenever the signal crossing from the minus VR2 to the minus Vm, so means a negative voltage, if you analyze across the D1, the negative voltage is passing through anode of D1 means a negative voltage passing through anode of D1, and the cathode is connected to your cathode is connected to the positive voltage here for a diode D1. So with respect to these 2 points, a negative magnitude is passing through the anode of D1 and a positive magnitude is connected across the cathode of D1. Hence, it satisfies the condition means what happens, your anode voltage is less than of your cathode voltage. Anode voltage is lesser compared with your cathode voltage. From this point of view, if the anode voltage is lesser compared with the cathode voltage, we know that the diode is enters into the non-conducting state. Hence, here the D1 enters the non-conducting state. So, if it is a non-conducting state, the state is represented as your off state here. So, if it is off state, then we need to replace with the open circuit model here. Similarly, let us assume the same signal is a passing through the diode also here means a negative signal is passing through the cathode of D2 here at this point. But what is the input here? Here input is less than or equal to minus VR2. So we are saying that your input signal here is a less than of a given negative magnitude DC reference voltage. Then, but anode side of D2 is connected to VR2. So from this point, what happens here? This region. So this region is acts as your more voltage means. So this is compared to your VR2. This is more positive compared to this voltage. That is the reason. What happens here from this statement? A lesser voltage of with respect to your given DC reference signal that is passing through your cathode of a D2 and some magnitude is passing through your D2 of anode. Hence, from this point, whenever Vi is just less than or equal to minus VR2, at this point, your anode voltage becomes greater compared with your cathode voltage for a diode D2 here. From this point of view, we know that, so what happens if the anode voltage is greater compared to the cathode voltage, we can say that that particular diode is acts as a conducting mode. Hence, at this point, diode D2 is acts as a conducting mode. So, if it is a conducting mode, that state is represented as your on state. So, if it is on state, it should be replaced with a short circuit here. So, hence, we observed when the input voltage is less than or equal to minus VR2, we observed that the D1 is acts as a non-conducting state and the D2 is acts as a conducting state. Hence, we need to draw the equivalent circuit based on this approaching. So, From that point of view, now we need to replace the diode D1 with the open circuit, and the diode D2 is replaced with a short circuit. Hence, here I'm going to redraw the circuit. Whenever the input voltage is less than of minus VR. So from this point of view, we observe that here diode D1 is acts as a non-conducting mode. Hence, it should be replaced with the off circuit, that is nothing but a open circuit. And at this point, whenever the Vi is less than or equal to minus VR2, diode D2 is acts as a conducting state, that is nothing but on state. If it is on state, it is replaced with a short circuit. This is short circuit model. Based on this equivalent model, now we are going to observe the output voltage across this given clipper circuit. So from this point of view, what is output voltage? Now this output voltage is proportional to this node here. So parallelly it is this node. So here this node contains some voltage source. What is the voltage source here? VR2. Hence, when if the Vi is less than or equal to minus VR2, the V0 is represented as your VR. But what is the VR2 magnitude? The VR2 magnitude is your negative magnitude. Hence, the output voltage across this given clipper circuit is minus VR2 here. Now, similarly, now we need to analyze if the input signal lies between this VR2 and VR1. So that is the reason I consider this statement. Whenever the input signal is passing through this VR2 and VR1, so what happens? We need to check it here. So from this point of view, so what is the statement? So minus VR2 is less than of Vi is less than of VR1. Means based on this statement, your input signal is passing in between the given two reference voltage levels, that is VR1 and your VR2. If you observe this first statement, so means Vi is greater than of, from this representation, what is this one? Vi is greater than of minus VR2 here. So the Vi is greater than of minus VR2 here. So what happens here? So from this point of view, what happens here? So if the Vi is greater than of minus VR2, so means, so this is which voltage we are applying here? A negative voltage we are applying here. Then again, Vi is less than of VR1. We have the 2 points. One is Vi is greater than of minus VR2. One is Vi is less than of VR1. So at this point, what happens here? If the Vi is less than of VR1 means a lesser voltage is passing through this anode of D1, but cathode is connected to VR1. But here, what is anode voltage? Anode voltage is less than of VR1 means D1 becomes your off state, non-conducting state here. Due to this condition, diode is D1 is non-conducting state. Hence, the state is represented as your off state. If it is off state, it is replaced with the open circuit here. Similarly, and your input voltage is greater than of minus VR2 means, so for this diode D2, a larger voltage is passing through this cathode compared with your anode. Hence, the D2 is also acts as your non-conducting mode here. So if it is a non-conducting mode, we can represent it as the D2 state is off state. Hence, the diode D2 is also represented as open circuit model here. So means that from these two observations, if the input voltage lies between VR1 and VR2, both the diodes are acts as your non-conducting state. Hence, both the diodes are replaced with the open circuit model here. So hence, I'm going to redraw this equivalent circuit here. So if your input voltage is lies between VR and VR1 here, under this condition, what we observed here, both the diodes are acts as your non-conducting state. Hence, both the diodes are replaced with the open circuit. So from this point, D1 is the open circuit, D2 is the open circuit. Now we need to observe the output voltage. So what is output voltage here? So V naught is so this output voltage is again directly proportional to your given input signal. Hence, the V naught is represented as your VI. So from this point, the V naught is represented as your VA. So up to this point, we identify the three statements here. So one is, so if so the first point is, if we observe if the VI is greater than or equal to VR1, the output voltage is VR1. And the second point, what we observe here, if VI is less than of minus VR2, the output is represented as your minus VR2. And the third point, we observe that if the input voltage is lies between a given two reference voltages, the output voltage is represented as your VA. So hence, so we need to draw this response. How we are going to draw this response? For this case, so suppose here I am going to make, let us assume that, and what are the parameters? If the VI is greater than or equal to VR1, output voltage we observe that VR1. If the VI is less than or equal to minus VR2, we observe this VI naught is equal to minus VR2. And if the input voltage lies between VR2 and VR1, the output voltage is represented as your VI. So these three parameters we need to show in a response. From that, we can say that it acts as your two-level clipper here. So let us take your input signal is, let us take this is omega t, and here it is I am representing a Vi. Let us take this is the maximum peak voltage, the Vm, and this is again negative magnitude, negative peak voltage here. So first here, we need to define your given reference voltages here. So what are the reference voltages here? We consider that VR1 as well as your VR2. And we taken that both the amplitudes are same, but the polarities, magnitudes, mean the polarities are represented as opposite polarity. Hence, suppose I assume that this is my VR1, means it also intersect this point. And similarly, we considered another reference voltage is VR2. So hence, I taken this is my VR2, but magnitude is different, polarity is different. Hence, it also intersect this point here. Now, just draw this intersecting points here. This is intersecting point, and this is intersecting point. Again, this is intersecting point, and this is intersecting point here. So from this point of view here, and from this node to this node, what happens here? So this node is acts as your Vi is greater than of VR1. From this point, so this voltage is acts as the Vi is less than of VR2. And in between, that is acts as your input voltage lies between VR2 and your VR1. Now, this duration, if the Vi is greater than VR1, what is output voltage? That is VR1. Hence, I am going to draw this output circuit, V0, output response, V0. So, if the input voltage is greater than or equal to VR1, the output is represented as your VR1. So, hence, so this is, and this portion, from this point to this point, and this is the input signal. From VR1 to Vm, input is passing from VR1 to plus Vm. Then we can say that this region is contains your input voltage is just greater than of your given DC reference voltage 1. At this point, the output voltage is represented as your VR1. So hence, I consider this is VR1. Then similarly, let's take this point from this minus VR2, whenever the input signal is passing from minus VR2 to minus VM, at this region, the input signal becomes lesser of your given DC reference voltage here. At this point, what we assumed here, if the input signal is less than or equal to minus VR2, the output voltage is represented as a constant DC magnitude, that is VR. So hence this region. So let us take this is I considered a minus VR2, and this region I consider as a VR1. So hence whenever the input signal is passing from minus VR2 to minus VM, but that particular region is acts as a the input voltage is less than of your given DC voltage. Hence, so the output voltage is represented as your minus. So here the output voltage is represented as your minus VR2. So this is minus VR2, and here this is plus VR1 here. Now remaining, so from this node to this node, so what happens here, this is input voltage lies between VR2 and VR1. Again from this node 0 to plus VR1, again this VR1 to minus VR2, again this minus VR2 to 0. These all these regions, the input voltage is lies between a VR1 and a VR2. If the input voltage the lies between VR2 and VR1, we observe that the output voltage is approximately equal to your input signal. Hence, and here the input signal is not a constant voltage, not a DC voltage, that is a linear voltage. Hence, we need to draw the linear signal. So hence, so from 0 to this VR1, so means the output is a VA. Hence, it is same linear signal. Again, from this VR1 to minus VR2 means if my input signal is lies between VR1 and VR2, output is represented as VI. Means how the input is going, the same way we need to take the output signal. Hence, from this node to your minus VR2, input is signal is linearly decreasing towards minus VR2. So hence, the output voltage is also linearly decreasing from this VR1 to minus VR. Similarly, and from this one, minus whenever the input signal is changing from minus VR2 to 0 voltage. Now, what is the condition satisfied? This third statement is satisfied. At this point also, the output voltage is equal to your input signal. Hence, from this point, whenever the input signal changing from this minus VR2 to 0 voltage, the output voltage is also linearly changes from minus VR2 to VA. So hence, this is your the same circuit I showed here. This one is here. So let us take this is my plus VR1, this is plus VR2 here. So here, if you observe this response, what happens here? It limits the some amount of the voltage in a positive portion. Similarly, it also limits the some amount of the voltage in a negative portion here. So how this response is we observed by by combining the positive peak flipper. So if you observe up to this 0 to pi duration, and this circuit is looks like a positive peak clipper with some positive reference voltage. Then if you observe this pi to 2 pi duration, it looks like a negative peak clipper with a negative reference voltage. We are combining this positive peak clipper with a positive reference and negative peak clipper with a negative reference. Then this type of the response is called as the two-level clipper. Means a some amount of the amplitude is limited in both the levels, positive level as well as your negative level. So hence, from this response, this type of the circuit is called as your two-level clipper. So up to this point, today we observed that what is the two-level clipboard and the analysis of two-level clipboard with respect to your characteristics of the two-level clipboard. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.